So let's look at another problem. So I think this is going to be our last and final work along relating to the first chapter with respect to understanding mechanical stress. So we've got this bar with a varying cross section. So the question states, the cross section of a bar is given by A is equal to into bracket 1 over x squared over 100 into bracket centimeter squared, where x is the distance from one end. Okay, so we're assuming that for any distance along the bar, that distance will be assumed to be x. We're being tasked to find the extension under a load of 20 kilonewtons on the length of 10 centimeters. And for this particular component, we're going to assume A to be equal to 200 GPa. So let's have a go working through this problem.
So let's work through this problem. So we've got this unusual component that has a varying cross section. We've got our axial load of 20 kilonewtons. Now what we're going to do is we're going to assume that this structure or this component is being extruded from a length 0 to a maximum of 10 centimeters. Okay. And what we're going to do is, since we have a situation whereby the area seems to be changing with respect to any distance along the component x, we're going to assume that the change in area with respect to any distance x will be equal to 1 plus x squared over 100. So this is the assumption that we're making. So we're going to call that equation 1. Okay. Thus, any small change in area will be equal to into bracket 1 plus x squared over 100 dx. So this becomes an integration problem. Okay, so once we integrate dA with respect to dx, that will give us some clear idea in terms of what the total area, total cross-sectional area of this component is likely to be. So therefore, working out the cross-section or cross-sectional area A, so dA will be equal to the integral from 0 to the final length, okay, into bracket 1 plus x squared over 100 dx. So the limit is basically the extruded length from 0 to the final length of 10. Alright? So again, we're integrating both sides, so we shouldn't forget. So the area is equal to 0 to 10 centimeters of 1 plus x squared over 100 dx. Okay. So again, we can integrate each variable with respect to x. Alright? So if we have y bar, okay, so this is some basic revision, is equal to x n, okay, so let's say dx, then the integral of y will be equal to the integral of x n dx. Thus, y will be equal to x n plus 1 over n plus 1, okay, plus c. So c's are constants of integration now. Because we've got limits, we don't need to worry about what the constant of integration is. Okay, so this is just some quick revision along the way. So A is equal to, so we're integrating each term with respect to x, so this would be x plus x cubed over 300, and the limit 0 to 10. Right, and this would be in centimeter squared. So what I'm going to do is I'm going to work it out in centimeters squared, and I'm going to convert it to millimeters squared. Alright, to make life easy for us. Okay, so if we put our limits in, this becomes 10 plus 10 cubed over 300 minus, so the lower limit, 0 plus 0 to the power 3 over 300. Okay, so this bit will work out to be 0, leaving this part. So this becomes 10 plus 1000 over 300 centimeters squared. So this becomes, so we can cross that, so 3 to that, it's about 3.33 recurrent, so let's just round that up to 4, so that becomes 13.3334 centimeter squared. And there we have it. So we've worked out the area. So the next part is to work out the stress. So the force F, that's given the problem to be 20 kilonewton. So that's more or less the same as 20 times 10 to the power 3 Newton. We've calculated the area A to be 13.3334 centimeter squared. So I'm going to convert that to millimeter squared by multiplying this value by 10 to the power of 2. Okay, so don't forget that 10 millimeters is equal to 1 centimeter. So this becomes 13.3334 times 10 to the power of 2 millimeter squared. Okay, and this will give us 1,333.3334. So let's go with that, millimeter squared. So therefore, the stress, that is small cat sigma, is equal to the force divided by the area. So this becomes 20,000 divided by 1,333.3334. Okay, so we'll have this in Newton per millimeter squared, which from previous examples is the same as MPa. So let's get our handy calculator to calculate the stress. So 20,000 divided by 1,333.3334, and that gives approximately 15 MPa. And there we have it. So now that we've calculated the stress, we can then work out the strain. Then once we've worked out the strain, we can easily work out the change in length or the extension. So we calculated the stress, and that gave 15 MPa. So let's not forget, M represents a million. We've also been given some information regarding the Young's modulus. So the Young's modulus, so that's our E, that was given as 200 GPa. Alright, so giga, that represents a billion. So therefore, the strain, so the measure of deformation, epsilon, is equal to the stress divided by the Young's modulus. So this becomes 15 10 to the power 6 over 200 times 10 to the power of 9. Okay, so don't forget that strain is dimensionless. So that goes into that 3. So we get our calculator. 15 divided by 20 10 to the power 3. That gives 7.5 times 10 to the power of minus 5. So we worked out the strain. So we're almost there. So since strain is equal to the ratio of the change in length or the extension divided by the original length, if we make delta L the sum of this equation, then that becomes the strain times the original length. Okay, and we shouldn't forget that delta L characterizes the extension. Okay, so we know that L is equal to 10 centimeters, which is the same as 100 millimeters. So therefore, delta L is equal to 7.5 times 10 to the power minus 5 times 100. Okay, which gives 7.5 times 10 to the power minus 3 millimeters. And there we have it.
So to summarize this particular problem, here again is a diagram representing the problem. So we've got 20 kilonewtons acting on the bar to cause the bar to elongate. We've also got or established some boundary conditions. So at 0 extrusion of the bar, we're going to assume that to be L0, which will be equal to 0. And the full extruded length of the bar, we're going to assume that to be L subscript F, so that'll be equal to 10 centimeters. We're also going to look at a small section of the bar. So the length of that small section, we're going to assume that to be dx, okay? And that small element in terms of the sectional area, we're going to assume that to be dA. Thus, we're going to assume that the small change in area, because the area is changed with respect to x, that small change in area with respect to x will be equal to the formula that we were given in the question. So dA over dx is equal to 1 plus x squared over 100 into bracket centimeter squared per centimeter. So this is what we're going to assume, and we're going to integrate the area to get the full sum of the cross-sectional area for this particular bar to work out the stress, the strain, and eventually the extension. So this is a quick summary of what we just worked out. So as I stated, we're going to assume that the change in area with respect to the change in x is equal to 1 plus x over x squared over 100 centimeters squared per centimeter. Thus, working out the area, we're going to assume that small change in area will be equal to 1 plus x squared over 100 dx. So if we integrate both sides, we have the integral of dA is equal to the integral limits from L0 to LF, so that is 0 to 10. 1 plus x squared over 100 dx. Okay, so therefore the area, if we integrate, will be equal to x plus x cubed over 300, okay, from limits ranging from 0 to 10. So if we substitute our limits into the equation, we end up having a value of 13.333 recurrent cm squared. So what I'm going to do is I'm going to convert from centimeters squared to millimeters squared by multiplying this value by 10 to the power of 2. And that gives us 1333.333 millimeters squared. And there we go. So now that we have that, we now have all the variables that we need, to calculate for the stress. So since stress is equal to F over A, so don't forget that F is the deforming load, which is 20,000, divided by the area, which was worked out to be 1333.333, that would give us approximately 15 MPa. So now that we've worked out the stress and we know what the Young's modulus is, we've got all that we need to calculate the strain. So strain, epsilon, is equal to the stress divided by the Young's modulus. So that would be 15 times 10 to the power of 6 divided by 200 times 10 to the power of 9. So if you divide 10 to the power of 6 by 10 to the power of 9, you're left with 1 over 10 to the power of 3. Okay? So we do the computation and we get 7.5 times 10 to the power minus 5. So that is the calculated strain. Since strain is also equal to delta L divided by L, so delta L is the change in length or the extension, and L is characterizing the original length or the extruded length of the bar, which is equal to 10 centimeters. Since I'm working the basis of millimeters, I'm going to change that from 10 centimeters to 100 millimeters. So the product of the two would give 7.5 times 10 to the power minus 3 millimeters. And there we have it.
Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session as we look at further examples relating to uniaxial strain. So please share and subscribe, and I'll catch you in the next section. Bye for now.